Would you like to learn more about writing your own tools and extensions for Aseprite in Lua, for example a custom character creator like this one? Well, you've come to the right place, because in this video we will go through the entire process from start to finish. If you haven't written any custom tools for Aseprite before, or you didn't even know that it is possible, you can definitely follow along this video, but maybe you want to first check out my previous video on Lua scripting in Aseprite, which I have linked in the description below, because there I cover some of the basics in more detail. To get started, we open our scripts folder from Aseprite like this. Here we create a new Lua file and give it a meaningful name, for example, character creation. Now we can open the file in Visual Studio Code and we are ready to go. The first thing we do is create a new dialog and capture it in a variable, which I will call DLG. Make sure to declare it as a local variable to limit its scope to only the script we are working on. If you don't know what that means exactly, feel free to check out my previous video in which I show what happens if you don't use the keyword local here. We create the dialog by calling the dialog constructor that Aseprite provides, and we pass it a string argument which becomes the title of the dialog window. We can also define the size of the dialog by setting its bounds property like this. Bounds is of type rectangle, so we assign it a rectangle with our desired x and y position coordinates, as well as width and height. We keep it simple and don't base these values on the current screen resolution for now, and instead just use some fixed values. Feel free to choose different values depending on your setup though. So how can we run this script now from Aseprite? We go to File, Scripts, and we click Rescan Scripts folder. When we go back to the same menu, we now see that our new script appears in the list. We could click it to run it, but let's set up a keyboard shortcut for it too, because this will make it much more convenient to test things while we are developing the tool. To do that, we go to Edit, Keyboard Shortcuts, and under Menus, Scripts, we can assign a key combination for our new script. In my case, I choose Ctrl, Alt, and C. Now, whenever we want to run our script, we can simply press this key combination. But wait, nothing happens. Is the key assignment not working? No, it's actually not that, but the fact that we don't show our dialog yet. So far, we only tell Aseprite to create one, and since it is local and runs out of scope when the script finishes, it gets destroyed afterwards. So in order to actually see the dialog, we have to call its show function, like this. Make sure to use the semicolon rather than a dot here. The semicolon in Lua means that the instance that calls the function, in our case DLG, gets passed as self to the function without explicitly providing self in the argument list. And since show is a member function of the dialog class and we want to call it bound to our specific instance DLG, we should use the semicolon here. Now let's test our script once more. And yep, here we see our dialog with the title that we provided and the size that we chose. Now let's fill our dialog with life, starting with the first button. The button should create a new sprite for us. So let's create it by calling the button member function of the dialog class, again using a semicolon. The button function accepts a table as an input argument. Tables in Lua are written with curly brackets, so let's provide a table like this. In that table goes an ID, which is a string by which we can identify the button in our script. Let's call it new. With text, we can provide the text that should be written on our button. Let's make this new character. And finally, we have to tell Aseprite what should happen when the button is clicked. We do this via the onClick property, which should get assigned to a function. This function we can also simply call new. But new doesn't exist yet, so we have to write it too. We make it a local function right above our button creation code. Note that Lua will not find that function if you put it below the button code, because the function is local, and Lua only finds local functions or variables that are declared further up in the script. We leave the new function empty for now, just to see if our button is created correctly. And yes, there it is. We can click it, but of course nothing happens yet. So what should happen when the button is clicked? Well, we want Aseprite to create a new sprite. We want a couple of layers being created. We want to load the images of the character parts which we can cycle through. And we want Aseprite to draw a character to get started with. We can type in all those things as functions like this. None of those functions actually exist yet, so let's create them. Let's start with the create sprite function. The sprite in Aseprite is actually the whole scene, so to speak. So a canvas with a color palette, different layers and frames. We want to do things with our sprite not only in the create function, so what we can do is declare our sprite outside of the function as a local variable above. In Lua, you can do this without immediately initializing the variable. It will be a nil value until you assign it a meaningful value. But at least we have now made the variable name known for the rest of the script. In the createSprite function, we can now assign it to a new sprite object with a width and a height. In our case, 32 by 32 pixels is sufficient. We also want to give the new sprite a file name, like this. So let's try this out. We can see that clicking our button now indeed creates a new sprite with the correct size. But there are still some strange things going on. The palette consists of only black colors, and the file name we provided is not yet shown in the tab. To fix the file name issue, what we need to do is to tell Aseprite to refresh by using app.command.refresh. When we click our button again, we now see that the correct file name gets displayed. So what about the color palette? We can load our desired palette by using app.command.loadPalette. In there goes a file name. So let's first make sure that we have a palette ready to be loaded. For this example, I have prepared a palette file in a dedicated folder beforehand. So in our load palette function, we can point to that file like this. The two dots here are Lua's way of concatenating two strings. So the string folder and the string characterCreation.pal are glued together as one string. However, folder doesn't exist yet, so we need to define it. We will need that folder in a few other places too, so it is good practice to declare it as a constant local string value at the top of our script. I like to use capital letters for constants, so let's write it like this. In the path string, make sure to either use forward slashes or double backslashes. A single backslash in a string is an escape character, so if you want to use a backslash in a path like this, we have to use two of them. When we run this code, we see that we are now getting prompted with a file selection dialog to choose our palette file, and that is not what we want. To prevent that from happening, we can pass UI is false to the argument table that goes into the load palette call. Now there is still another unwanted thing going on. While our dialog is open, we can no longer interact with the rest of Aseprite. For example, we cannot zoom into our sprite, which is quite inconvenient. Luckily, this can be easily fixed like this. In the show function for our dialog, we've provided a table, and in there we say weight is false. And now that we provide a table, we don't necessarily need the round parentheses anymore, so we can leave them out. And with that small adjustment, we can now zoom in and interact with Aseprite while our dialog is open. Another thing we want to set up for our sprite is its color mode. As you can see, by default it creates our sprite in RGB mode. For a character creation tool like this, we want to easily adjust the colors of the different character parts by tweaking the colors in the palette. So indexed mode is much more convenient in this case. So how do we set indexed mode for our sprite from script? Well, this is another app command called change pixel format. We pass it a table with a property format and we set it to the string indexed like this. Now when we run our script again, the index color mode is indeed set. One last thing we want to do is to set up the background color for our sprite. In my case, I would like it to be black rather than transparent, and we want it to be a proper background layer rather than a regular layer. We can do this as follows. app.bgcolor is, and then we create the color black like this. Also, to turn the layer of our sprite into a background layer, we can call app.command background from layer. With those changes, we can now see the sprite in black, and the layer is indeed a background layer that automatically gets the name background. Now we have everything set up for our sprite, so let's turn this into a character creation tool. The first thing we need is the layers for the individual parts of the character. So in our create layers function, we set up a for loop, which does something for each character part like this. Here we use Lua's iPairs iterator, which can iterate over an index table and return each index and value combination in the correct order. For each part, we want to create a new layer like this. However, the parts table does not exist yet, so let's create it as a table of constant values up in our script, where we also declared the folder. Each part we want to be a table with some data. For now we only need a name for each part, but we will expand this table a bit later in the video. So let's type in the name of each part that we want our characters to consist of. In our create layers function, we can now set the name of each new layer to the name as defined for that part, which we can get from the iPairs iterator like this. And when we run this, we get an error. Well, actually yes, because I had a typo here. The new layer function is spelled with a lowercase n, so let's quickly fix that. Let's run it again, and here we have our layers. But wait, the layers seem to be in reversed order, with the hair layer being at the bottom. Well, this is because the new layer function stacks the layers on top of each other. To fix that, we can adjust the code like this. Instead of the part as it is returned by the iPairs iterator, we can access each entry in the parts table by counting backwards based on the current index I. The hashtag operator here is the number of elements in our parts table. Please note that Lua counts things from 1 upwards, not from 0, like many other programming languages do. So in order to access the correct element, we actually need to add 1 here. And with this change, we no longer need the part as it is returned by the iterator, so we can also remove that to clean things up. With this, we now have all layers in the desired order. The next function we need to fill is load part images. Again, we want to do something for each part, so we can prepare a similar for loop as before. For each part, we want to load a PNG file that contains all the available options, similar to how a tile sheet would be set up when creating tile maps for a game. Aseprite provides a class called image, so we can use that one here. By using the from file property of the input table, we can point to a PNG file that contains all the available options for the given parts property. For example, all hair parts. But of course, we don't want to spell it out explicitly for each part and instead use the part.name property here. If we write it like this, the PNG will not be found though. This is because in our parts table, we wrote all the parts with capital letters, and the PNG files in our folder use underscores between each word. We could of course change the names of the PNG files, but let's keep the names like this and instead see how our code can be made compatible with this naming convention. First, we want our part names to be turned into lowercase. We can do this by using the string.lower function that Lua provides. Second, we want to replace all white spaces in the resulting string with an underscore. This can be achieved by using the string.gsub function. It takes as a first argument the string we want to modify, then the character we want to change, in this case a white space, and then the character we want to replace the white space with, in this case an underscore. And I made a small mistake here again using regular parentheses, because actually the input to the image constructor is a table, so we need to change them to curly brackets. So now we have loaded a PNG image for each part and stored it in a local variable called image. But we will need access to those images more often, not only within this function. So let's store all those images in a table that we can also access from outside of this function. We can call this table part images, and we will make this a key valued table. So each part name we can use as a lookup key, and as the corresponding value we define a table with all the data that we need. Before we decide which data we need, let's first declare the part images table on top of our script, where we also declared our sprite variable. Now, what do we actually want to store in there for each part? Well, for each part, we want to store all the available part options. Up until now, we only have one image per part that contains all the options next to each other like in a tile sheet. But now we want to split the content of that image into smaller chunks and store each chunk separately. We can do this by writing another for loop, which traverses the content of the image. So we can use an index variable I and let it run from 1 to, well, the maximum number of part options in the image. And that is the total width of the image divided by the width of each of the part options in the image, which I call part width here. Part width doesn't exist yet, so let's declare it as a local constant at the top of our script. The value it needs, of course, depends on how you have drawn your part images, but in my case it should be 11 pixels wide. While we are at it, let's also immediately define the corresponding part height constant, which in my case should be 8 pixels. Now, within our for loop, we can insert into our part images table for the given part name a new table, which will be the result of yet another helper function called getPartImage. In that helper function, we can do the actual splitting of our parts image into the desired chunks. So each chunk or part image will be a new image. And the size of that image is our previously defined part width and part height. To get the desired chunk from our full image into our new part image, we can use the draw image function like this. In there goes the full image, and we don't have access to it yet, so we need to also provide the image as a parameter to our helper function like this. And also the coordinate at which we want to cut out our chunk. You can think of this mechanism as a small window within our image, which has part width and part height size. And with the coordinate that we now provide, we can offset the bigger image around it while keeping the window fixed, so that the different chunks we want to cut out are shown in that window. The coordinate is once again an instance of point with an x and y. The y coordinate is easy. It's just 0 because our image is just listing all part options horizontally, so we don't need to move the image in y direction. But what about the x coordinate? Well, that one depends on our loop index I, doesn't it? Oh, and by the way, I made another small mistake here. Do you see it? I have two nested for loops here that both use I as a looped index, and that's not good. We could rename the second one into j, for example, but actually we don't really need the first one, so now we can also just replace it with a blank symbol, which in Lua is an underscore. This way we can keep I as the name of our second loop index without any naming conflicts. And this I variable we can now pass to our helper function like this. To offset the entire image in x direction, we can define the x coordinate as 1 minus I times part width. And the last thing our helper function needs to do is to actually return the part image that we just extracted from the bigger image. And now we can finally draw our characters on screen. To do that, we go to our still empty draw function and we loop once more over all parts. In that loop, we can extract the part image that we want to draw from our already prepared part images table for the given name we are currently looping over. But wait. Part images of part name is actually not an image, but again a table of all the options that are available for this part, right? So which one should we draw? Well, that will depend on what part option the user has currently selected. So in here we can type selected parts for the given part.name, and this is once more a table that we first need to define on top of our script. So up here we prepare selected parts as a table in which we store the index of each currently selected option for each part. So if the user has selected hairpiece number 3, for example, selected parts of the string hair will be 3. We have yet to implement the actual selection buttons for the user, but we also want to have a default selection when the tool is started up. So let's initialize our selected parts table by storing index 1 for each part. This means that when the tool is first started up, we want to draw a character that uses the first hairpiece, the first headpiece, the first upper body piece, and so on. Now back in our draw function, we want to draw the part image that corresponds to the current selection. In order to do that, we need to tell Aseprite in which layer, in which frame, and in which cell we want to draw. The layer is determined by the part name, so we can access all layers of our sprite like this, and then point to the one that matches the part name we want to draw. The frame and the cell are less complicated in this case. We only have one frame, so we just take the first one like this, and the cell then follows from the provided layer and frame like this. This is actually enough to get the correct cell. The code that I added in the same line here is actually not needed. At the time of recording, I still thought it would be needed to create and initialize the cell the first time that we want to draw something, but I later saw that it actually works just fine if you leave that out, so you can ignore that part. Now that we have the cell, we can clear its image to remove any content that is already drawn, and then call the draw image function like this. The first argument is our part image, and the second is the position in our canvas where we want to draw. Now, the Y position at which we want to draw actually depends on which part we are drawing, right? So let's tell Aseprite to draw it at Y position part.Y position. And in order for that to work, let's add for each part our desired Y position in the parts table at the top of the script. You can play around with different values depending on how your images look like, but these were the positions that worked for my example. Now, what about the X position? Well, we want to draw the character in the center of our canvas, so we need half the sprite width and subtract from it half the width of the part image. And we can make this calculation a bit nicer by performing the division by 2 only once, like this. The last thing our draw function needs to do is to refresh our app and to repaint our dialog. So let's test if our draw function does its job. Well, actually no. We still see a black canvas and no character. Why is that? Well, this is actually due to another mistake I made in the beginning in our create sprite function. Remember that we told Aseprite to set the sprite to index mode? Well, we actually need to do that before we create the sprite, otherwise we will not see anything. So if we move that line above the first line in the create sprite function and we try again to run our script, we finally do see our character. Now the last thing we need to do is provide some buttons for the user to cycle through the different part options. So down here below our our button that we added in the beginning, we want to add for each part a previous and a next button. So again, we need to loop over all our parts and for each part create those 2 buttons. As text for those buttons, let's use a left and right triangle arrow. You can look up the ASCII codes and check your machine settings to type them in directly in Visual Studio Code, or you just copy paste them from somewhere. Let's leave the on-click functions empty for now and try it out. As you can see, it does create the buttons, but Aseprite puts them all in the same row, which is not what we want. We can fix this by adding a separator between each button pair, with the text for each separator being the part name it corresponds to. This looks much better, right? And now we need to implement the on-click functions. What should happen when we press next is that we increase the index of the currently selected part by 1, like this. When we try this, it does seem to work, except that it doesn't really, because when we are at the last option in our parts list, which in my case is index 5 because we have 5 options per part, increasing it by 1 makes it 6. And our selected parts subtable for the part does not have 6 entries. This is why we get an error when we try to press next one more time. So instead of simply adding 1 in all cases, we actually want the selection to wrap around. So we wanted to start over at index 1 when we have reached the end of the list. For these kind of wrap around computations, the modulo operator comes in handy. In Lua, the modulo operator is written as a percentage symbol. Without going too much into the mathematical details of this operator, just remember that it provides the wrap around functionality that we want here. So instead of simply adding 1 to the current index, we first take the current index modulo the maximum allowed index, which is the size of the table that contains our part images, and then add 1 to the result. Again, because Lua starts counting at 1 and not at 0. When we run the script, we can now safely click next as often as we want without any errors. For the on-click function of the previous button, we do something similar, except that the formula is slightly different as we are cycling backwards through the list. And this is how it should look like. And with that, we have our character generator ready to be used. So now you can easily create all types of combinations for your game characters. But probably you also need a tile map to create the world that your game characters inhabit. And if you want to know how to create those directly in Aseprite, check out this video next.